Thanks so much for coming out tonight. I'm really happy to see you all and to talk to you today about dark matter and specifically how we can search for dark matter using the biggest collider in the universe. And we've already had a really good head start with those sequence of videos and all this stuff about rotation curves, but to start with my talk today, I thought I'd step us back a little bit and say, how do we know anything? Which might seem like a little bit too much, but let's see where we can go. So I think if you think about science in general, you can trace the origins of science to early writers, and one of the writers I would like to highlight is Iguana, who was an Akkadian author. In fact, she is arguably the first author. And when we do things in science, like we write papers, we often, like in certain fields, astronomy in particular, talk about who's going to be the first name of authorship on a paper, and this is the first author when you write papers. In particle physics, actually, we just do things alphabetically to avoid any sort of disputes or arguments. And so this is actually maybe the first author, as in the first known author who wrote something down and whose name is known. So this is a different kind of first author. And among other things that were written about at the time, Iguana wrote about astronomy, or what was known about the movements of the heavens at the time. And there's a quote from her, the true woman, Nisaba, who's kind of, in a sense, the Akkadian goddess of knowledge and the hunt, a little bit like Athena from what I can tell, although I'm not an expert on this. So this very learned godlike figure applies the measure to heaven and places the measuring rope on earth. And to me, that's a sign that there's already something along the lines of scientific thinking taking place. So if we look at the disk off to the right, this is not from the same culture, but from a culture around the same period. And it's a little disk that you can put up to the horizon to see where the sun rises and sets, and see where the sun will intersect with the horizon over time. So this is, I would say, the first example of people trying to measure things, trying to make sense of what we see on Earth based on what we see in the heavens. There's one more thing I would emphasize, which is this is the city of Akkad, which was the Akkadian capital in 2300 BCE. And this is also necessary. It's necessary to have a very vibrant, rich culture, have a very developed society before you have time to sort of sit back and try to measure and figure out how things will happen. You need some sort of a rich history and a rich culture. The next thing I'll say, which maybe you'll feel is surprising coming from a scientist, is that augury and astrology, so the practice of looking at birds and trying to figure out what's going to happen in the future, looking at the stars and trying to figure out what's going to happen in the future, they both have the shape of science, but they don't have the same fact-checking. And so you can see this sort of thing in all sorts of cultures all over the world, and I would say that's sort of the beginning of science. So then some figures you perhaps have run into or heard about sort of came onto the scene. There was Pythagoras with the Pythagorean theorem telling you how to relate the sides of a triangle that has a right angle on it. There was Euclid, who wrote down a lot of the things that the somewhat interesting Pythagoreans who hated beans, they absolutely despised beans. So if you don't like beans, you would have made a great Pythagorean. So Euclid decided, hey, these people, they're a little bit odd, but they have a lot of good ideas about how shapes align. So let me try to write all those down. And the very beginning of Euclid's book on geometry, this is sort of the first geometry textbook, or one of the first, is very interesting to me, because I think it brings into existence something that's really important, which is in science and in mathematical knowledge in general, there are all sorts of paradoxes and abstract things that we have to understand in order to model the universe. And so the first statement is Semeon estin ou meros othen, which means a point is a thing that has no part, which seems almost paradoxical. It's almost saying that there's a thing that has no thing. So what he's just trying to define is, how do I define a point in space, or a point in a geometry and say it's existent in a spot, but there's nothing around it. It has no part. It's the smallest thing I can define. So this actually will come up at least 2 more times in my talk. I won't point it out, but if you want to, in the end, you can sort of ask me a question where this sort of point problems are coming up. It'll happen at a few points in my talk. Anyway. All right, and then the last character who perhaps you've also heard of, maybe not, is Ptolemy. So Ptolemy took this geometry and said, okay, there are many systems people have tried to use to measure the stars. Let me try to use geometry to measure both the stars and the planets and see how they move around. And famously, what Ptolemy found was that he saw the planets moving around, but then they did these sort of like back curves, these recursive movements, and he had to model them with what were called epicycles. So more on that in a little bit. Okay. At the same time, people were also coming up with ways to detect things that are far away. And a few great examples of that are also single name characters, because in early history you just have one name. That's all that survives. And of course, everything is a little bit apocryphal, and it's hard to keep track of exactly what happened. But in any case, there was Mozi, and Mozi was a Chinese thinker and scholar. All these people are pretty broad in what they're doing. Who is credited with having the first description of a camera obscura, or a way to transpose an image through a pinhole, depicted there. And then, really amazing to me, and something I only found out later in my scientific career, there was an early example of a seismograph, something that can detect waves in the earth, sound waves moving through the earth, earthquakes actually, using a sort of interior pendulum device, people think, when they tried to reconstruct what Zheng Hong did. But no one's actually 100% clear on what exactly happened. Sometimes you have to rebuild what the ancients were doing in order to figure out exactly what they were up to. But anyways, he could detect which direction an earthquake was coming from using an early detection device. And you'll see it'll look very similar to some very advanced devices we'll look at later. Okay, so now I'll take you to the next point in the story that we'll jump to. And don't worry, we'll move faster. If we move as slowly as we've been moving through time, we'll be here almost an entire civilization's worth of time ourselves. So there were a number of people who looked at the planets and looked at the Ptolemaic system of just looking out on the sky and charting their paths, and said, we're not quite 100% happy with that. What if we come up with a different system where instead of moving in these strange paths, we can instead think, let's, instead of putting the Earth at the center of all these bodies, put the sun at the center of all these bodies, and then see what happens. And of course that clicked. Things worked out a lot better when people modeled things that way. And then Newton, I would say, took up Enheduanna's call to take what you measure in the skies and bring it down to the Earth. And what he did was he wrote down an equation that works both for the orbiting planets around the sun and for gravity as we see it on Earth. So it's a single way to describe both. He also wrote a lot of other books about how things move and how things are. And at this time, I would say one of the important things that doesn't get emphasized enough is people started thinking about how they were thinking and how to crystallize rigorous thought in general. So let's go through a few quotes from that time. So there's Margaret Cavendish, who was an early natural philosopher, scientist, or someone thinking about how to do science. She has a few good ones. Nature is material or corporeal, and so are all her creatures, and whatsoever is not material is no part of nature, neither doth it belong anyways to nature. And also, nature is so full of variety that our weak senses cannot perceive all the various sorts of her creatures. And this is true. Part of science is coming up with models, coming up with an understanding of things that you can't directly access with your normal senses, and then coming to an understanding of them. And then Newton has a long one. He tended to write in a very long-winded fashion. This particular quote is from the Optics. And it's, as in mathematics, so in natural philosophy, the investigation of difficult things by the method of analysis, so teasing out what you're seeing, ought ever to precede the method of composition. This analysis consists in making experiments and observations, and in drawing general conclusions from them by induction, and admitting of no objections against the conclusion, but such are taken from experiments or other truths. For hypotheses are not to be regarded in experimental philosophy. So they're working out, how do we set up a system to look at things around us, come up with ideas about how they are, and then figure them out. Now, as we move through the centuries, people distilled what these early scientists were driving at into simpler terms. And so there's a great quote from Richard Feynman from the late 20th century that sums it up. It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with the experiment, it's wrong. And that's a really good summary of what we're up to in science. Okay, so what are we up to in science? What did we get up to after this? Unfortunately, I can't take you through step by step every piece of the history. But let me summarize as quickly and as best I can and try to tell you what I think are the most important pieces. So first of all, everything around us, neutrons, is made up of neutrons, protons, and electrons. Everything you see around you. Some things you don't see around you are made up of other things, but we'll get to those in a second. So this includes all the elements, all the molecules, and everything else around us on Earth. They're made up of neutrons, protons, and electrons. So electrons, perhaps you've heard of. These are the things that you can roughly think about moving through the wires in electric devices. Protons are sort of the nuclear, the middle part of an atom. They're much heavier. Neutrons also sit there with protons, but whereas protons have a charge like the electron, the neutrons are neutral. So we did an okay job naming those. The next thing we need to jump through is that there's an equivalence between mass and energy. And you may have heard of this equivalence as E equals mc squared, but I would say that's outdated. And nowadays, it's equally valid just to say E equals m. Energy literally equals mass. If you have enough energy, you can make new things of a certain mass. So if you have enough energy, if you build up enough, you actually have enough to make new things. So here I'm showing you two protons coming into some sort of space, some sort of region, and they make some new things. All right. So that brings us to the deeper layer that we've uncovered, which is the standard model of particle physics. And so it turns out you can think about those protons as being made up of quarks, particularly the up and the down quarks shown there. But then we've also discovered additional quarks, the charm, the strange, the top, and the bottom. We call these different flavors of quarks. And so, unfortunately, they weren't named after flavors, but being good grad students, when I was in Hawaii, we were sitting around one day and we said, what could their flavors be? And the best ones we came up with were umami, dill, cumin, sweet and sour, teriyaki, and barbecue. So you can just remember the flavors that way. Then there's the electron that we already talked about down to the left there in red, but it has some heavier copies of it, the muon and the tauon. They have all the same properties, they're just a little bit heavier. So if you wanted to make them, you'd have to put in more energy. And then we have neutrinos, which you'll get lots of talks about from the McDonald Institute, because the McDonald Institute is literally the epicenter of neutrino science in the world, in a certain sense. We've made some of the biggest discoveries in the last few decades. These are extremely light particles. They're also neutral, like the neutron. The neutron isn't even on here, because the neutron's also made up of just of those little quarks. Then in the green there, we have the force carriers, the photons, so that's light that you see around you. The gluon, those exist in nuclei and have a very strong force at short ranges. And then our weak bosons, our Z and our W, you don't see those very much at all, they're very weak. And lastly, there's the Higgs. And so what I'm going to show you next is a video. It'll have some wonderful music, and feel free to dance if you feel so inspired. And I'll narrate it a little bit as we go through. And this is showing you how we've uncovered all these basic properties of nature. Oh, can't skip this video. All right, so this is CERN. Although Canada and many people in Canada are part of CERN and are part of this experiment. I also spent 3 months here when I was a postdoc. So this is the Large Hadron Collider at CERN. So we can zoom in to the beginning of the Large Hadron Collider, which protons with protons, and see what they're up to. So they start with a tank of hydrogen gas, and they send that hydrogen gas through a little thing that strips off the electrons, and that means that it's just protons left over. And so there's this proton synchrotron booster that now the protons are spinning around inside, and they're using special electromagnetic waves to make the protons go faster. But that's enough. Next, they put it into the proton synchrotron to make the protons move even faster. And so then, you guessed it, after that, they have to put it into the super proton synchrotron to make them spin even faster. And so at this point, you might say, we've spun them up, they're moving very fast, so surely we're done, right? No. We're going to send them through another ring to make them move even faster. And only at this point are we happy. And so they're moving fast enough, so we start together. And they're hitting each other at such high energies that they're making new particles. And so we have 4 detectors set up, CMS, Atlas, and Alice being some of the main detectors. And so every collision gives you some number of particles that hit your detector, and then you have a bunch of data. You may have heard in the news over the last few decades that CERN invented the internet. This is kind of like a meme a few decades. And there is some truth to that, because CERN had to develop all sorts of information architecture to just process all the data that's created when you hit these protons together and have them rushing through your detector and firing off in all sorts of different ways that you have to analyze. So the task of analyzing is actually not trivial. We require thousands of scientists literally across the globe to take the data in at various data centers and then look at each one of these events and figure out what's happening with each one. Now over time, actually it takes years to collect enough events, and most of the events just show you normal things that you expect in the standard model. And those normal things give you that line that you're seeing, but you see a bump above the line. And that bump above the line indicates that there's a new resonance, a new particle that you've discovered. And in the case of what you were just shown, the new particle that was discovered was the Higgs boson. And this is just showing you for fun 2 little gluons that we talked about inside nuclei, zooming off and give you a spray of. So that's the Large Hadron Collider, and this is the kind of process by which we would discover new particles and figure out all the pieces of the standard model. So let me show you something else. We've been talking about these objects, which are the smallest pieces of nature that we understand so far, as particles. But really, the most modern understanding of them is that they're not really exactly particles. They're more like fields. And you can understand that as being a consequence of needing a conversion between energy and mass. So that the way that we mathematically model this is, over on the left here, we have 1 proton. So that's 3 quarks, which make up the proton, and 1 electron. So together, that's 1 bit of hydrogen over on the left-hand side. So if I were to say, what's happening when light goes from 1 atom to another atom? Well, you can see that as being as there's a light field or a photon field that exists everywhere. But if you put energy into it by letting the red electron fall into the proton, you can create a green particle, a photon, if you've fallen in with enough or a certain amount of energy. Then that green thing can come and hit the red thing, which is the electron on the other atom, and cause it to bump up. So when you look at actually how particles are interacting, it's actually like they're little excitations on an omnipresent background of a field that exists everywhere. And that's what I have to tell you about before I can really tell you about what the Higgs boson that we discovered at CERN actually is. So it's kind of like the field's field. So it's a particle that not only exists as everywhere like a field in space, but unlike the other particles, it actually has a non-zero value everywhere in space. And because it has a non-zero value everywhere in space, when other particles move through it, they're slowed down a little bit, or they interact. And this is where all the masses of the particles, where their intrinsic amount of energy required to create 1 unit of them comes from. Okay, so that brings us to the end of all of particle physics, which we got through in only like 10 minutes, so good job, everyone. And so we'll return to the hearkening of our first slide and go back to space. So meanwhile, back in space. So at the same time that we figured out all these things about the particles and the fundamental bits of nature, what we've also figured out is something really interesting, which is that when I look at objects very distant in our universe, and particularly when I look at other galaxies, which are more distant than anything in our galaxy, what I see is that as I look farther and farther away, the light emitted by those galaxies redshifts more and more. And what that is a signature that our universe is expanding, that space itself is stretching, so that when photons are emitted from those hydrogen atoms that we were just talking about in a galaxy far away, they don't reach my telescope with the frequency or the energy I expect, because the light waves have been stretched. And this is called redshifting. And Edwin Hubble discovered that there's this nearly straight, we found out eventually, but to people at the time it appeared perfectly straight relationship between distance and what you can think of as redshift, or how much this wave is stretching. And so it looks like our universe is expanding. And so this was the first really excellent piece of evidence for what you've heard about with Big Bang cosmology. So let's look at a few videos of Big Bang cosmology. So we'll look at one. One is from NASA. This one doesn't come with audio, so you'll just have to watch. The universe is expanding. We get a bunch of stuff. It's apparently turned into galaxies. And then we're sort of floating through the galaxies. So I'm going to ask you which one you think is a better depiction. I'm about to show you a second depiction. So here's the second depiction. I don't need to introduce it as much.
This was in a hot, dense state that nearly 14 billion years ago expansion started. Wait, the earth began to cool, the autotrophs began to drool, Neanderthals developed tools, we built a wall. We built the pyramids, math, science, history, unraveling the mystery that all started with a Big Bang. Hey!
So who preferred the first one? Who preferred the second one? I would say the second one is not only better from an entertainment perspective, it's actually more scientifically accurate, oddly enough. So the NASA one, if you look at it, it takes so long for that bang to happen, and then when it does happen, you feel like you're outside of it and it rushed towards you. When you look at the Big Bang Theory one, I think you feel more like you're inside of it, and it happens at a time scale that's extremely rapid.
As the expansion started, wait, the earth began to cool, the autotrophs began to drool, Neanderthals.
All right. So I have to really move fast because I don't have you for a full semester's worth of lectures, and so I have to get next to a problem with this whole cosmology, with all these things we saw around us. That Vera Rubin first crystallized in the 1970s. And this was already covered a little bit in that pre-video you saw. And what Vera Rubin discovered is that if you start measuring the velocities of things in galaxies, stars, gas, and you look at what those velocities are as a function of radius from the center of the galaxy, so that's what's on the x direction here, on the y direction is its velocity, you notice something very puzzling. So first, let's just establish galaxies rotate. And so what this is showing you is a fast rotating galaxy and a slow rotating galaxy. Actually, it's showing you what things would look like at low redshift and high redshift, but we don't need to worry about that to get to our point. What Rubin discovered is that based on the observations you can make, and based on that Newtonian principle of gravity, that tells you how much force is on something, and therefore how fast it would be moving, as a function of the mass contained inside of the region it's in. What Rubin discovered is there isn't enough mass in the stars, there isn't enough mass in the other visible matter in the galaxies for them to stay together. And so you can look at a plot like this, where you have the speed of stars in one direction, and the distance from the center of the galaxy in the other direction. And along that dashed line is how fast things should be moving if all the things there are just the stars or the gas. But instead what we observe is a lot more rotation, which means there's a lot more mass. And there's a very simple illustration of this that I can show you. So you can think of all these kids on this merry-go-round as stars, and you can think of them grabbing onto the merry-go-round as gravity. And if there's not enough gravity, by the way, hopefully this sounds
We don't know. We haven't listened to enough of them. So if there's not enough gravity, then that one. By the way, I don't keep the whole video, but he's fine. He actually jumps back on later in the video, so don't worry. Okay. So there's another way that we've seen
that there's something which, of course, we're going to be saying is dark matter. And so to introduce that, I first have to say gravity bends light. And so if I think about light coming from an observed stellar position, if there's a star in the way, for instance, light will bend around that star. And what this means is, if you look at starlight, or if you look at the light from distant galaxies, you can use the bending of that light, or how it actually changes the shape of the galaxy as it bends the light around it, to see where massive things are. And so when we've looked at things like the Abel cluster, we've actually been able to take how lensed galaxies, and some of these are lensed, and perhaps you can see that there are some elongated streaks in this. Where those elongated streaks are, we've been able to reconstruct where there are centers of mass. And when we color that in blue, in this diagram, what you can see is that there are centers of mass where you don't see stars. And sometimes this is called a bullet cluster phenomenon, because you often get this in regions where galaxies hit each other and move to other locations, and then you just get leftover clumps of mass. And this is another sign that there's something there that we don't quite understand yet. There was a hand in the audience, and I'm happy to take questions.
Yeah, I didn't know you were happy to pull this back down. But I was thinking, how do you even know that this is like some mysterious matter, not just a cold gas cloud that's also like, let's say, very diffuse as well, like a low pressure cold gas cloud floating out there in space altogether by gravity? I mean, would it require really some exotic matter to explain? I mean, if its density is quite low, it wouldn't interact much with light, so it wouldn't observe it directly. And if it's really big, though, it might still bend distant light, I'm guessing, by gravity. So why not just have a giant molecular cloud like?
So the key here is we know the properties of matter to an extraordinary precision. We know the properties of all the known matter. And so when we're measuring what's going on with galaxies hitting other galaxies, we can say, if there was the kind of stuff you're talking about, if there was any matter like we've ever seen in our laboratories or built up in a collider, it's a very good question, the one you've asked. If it's anything like we've seen, then it should have this large of a cross-section to interact with itself. And then it doesn't. So what we can see in those bullet clusters, for example, is that there's a bunch of mass that moves where it wouldn't have moved if it were normal matter. There's also ways that we can test for what the gas content is using different things than visible light, using radio frequency light. So there are lots of checks to this. And then there's additional cosmology ways that we can see that there's dark matter that I'll get to in a second. But your question is an absolutely spot-on one. And let me come to my next slide because it addresses it a little bit. Because this is the game that we play in dark matter, which is, this is my cat Wasabi. He was on the poster, by the way. And it's absolutely natural at this point to be skeptical. Like, what are we doing? How are we looking for things? And so I thought I'd show you a video today, which a lot of the scientists in the audience probably won't be able to get out of their heads after this, because it very cleanly encapsulates a lot of what we do. And I don't think many of them have seen it. Actually, I don't think many people in the audience have seen it. It's a video I grew up with as a kid. But it'll give you a sense of what it is like to look for dark matter. So the characters in this video are missing something, and let's see what they have to say.
Eliminate us. I went to Cat Tech, where I studied the same. What other cats do you know who can make such a claim?
Very well, Dr. Calculatus. Find it and eliminate us yourself.
I shall indeed. When you've mislaid a certain something, keep your cool and don't get hot. Calculatus eliminatus is the best friend that you've got. Calculatus eliminatus always helps an awful lot. The way to find a missing something is to find out where it's not. It isn't here, I'll mark this X. It isn't there, I'll mark that Y. It isn't underneath the apple, mark the apple HKI.
It isn't in this keyhole.
No.
And it isn't on my knee.
Mark the keyhole K300, mark the knee 57B. We just jot down all the places where it isn't, and gee whiz, very shortly we will locate where the missing object is.
It isn't here.
842J.
It isn't there.
F607. You can mark the piano 22,000 decimal point 11.
It isn't in the icebox.
That's strange.
It's not on this TV.
Icebox 024.5. TV 1,000,003. When you've mislaid a certain something, keep your cool, don't go to pot. Calculatus eliminatus is the best friend that you've got.
Calculatus eliminatus always helps an awful lot.
The way to find the missing something is to find out where it's not.
All right. So what is dark matter, though? And the answer is that's actually a pretty good performative answer because we have a lot of feedback we don't know. But anyways, the answer is we don't know. But I can show you roughly where it isn't. So if I look in terms of the mass of the particles here, and I look in terms of the mass of known particles, this is the neutrino mass roughly, the electron mass, the proton mass. If you've heard about weakly interacting massive particles, or WIMPs, which are a very popular dark matter candidate, they would fall there in mass. Then you can think about like little tiny bugs, like the little space bug I have there as being a mass. A mouse is a mass, an elephant has a mass. These are all perfectly fine masses for what the dark matter state could be. Even a solar mass is okay. Dark matter could actually be in clumpy objects of a solar mass. And then it could actually be even much lighter than this. But if it's much lighter actually than the electron, it turns out it can't be very large, or it can't be very interacting with a detector, because then stars would emit that dark matter candidate, and they would burn out faster than we see them burning out. So that gray region actually covers a lot in that sense. So we need very weakly interacting dark matter if it's very light. Then as we get heavier, there's a larger size that it can be relative to detectors. And so for the WIMP, for example, it can't be any much bigger than 10 to the minus 23 centimeters, which is an insanely small number. So that's a billionth of a billionth of a billionth, and then you still have to take 100th of that, of a centimeter, is how big the dark matter can be based on these very exquisite detectors, these very intense studies that we've done so far. You can actually also say that there's a minimum size it can be from gravitational details, which I'm happy to talk with you about afterwards. Then there are some really fun ways you can look for it that I'll talk a little bit about now. Okay, so this slide is here to provide a pause. And it's here to provide a pause because this probably looks like the cat we saw before, but it's not. This is the cat's sister. This is Paprika. That first cat was Wasabi. This is just to alert you to the fact that when you start looking at dark matters, they can look similar, but they can be different by very subtle ways. So just pay attention to that, because now we're moving on to a specific kind of different dark matter model that I've been studying with grad students and scientists here at Queen's University. And so what we've been looking at for the last 5 years or so is what we've called heavy assembled composite dark matter. And this is dark matter that would fall into the mass range of a bug, a mouse, even up to an elephant in mass. And it would operate a little bit similarly to the matter we've seen around us, in the sense that it would come together and form clumpy objects in the early universe, like in our universe, nuclei form at the inception of the Big Bang. So this is work I've done with Javier, Yilda, Chris, Gopi, Narayani, Katerina, and Rohan, who are all excellent young scientists. So I'll tell you about one possibility just to pique your interest a little bit. One thing we've been thinking about lately when it comes to these very massive dark matter candidates is if dark matter is big and loose enough, it could fall apart when it hits the Earth. And we've started calling these loosely bound composite dark matter candidates. And so this is when the dark matter is pretty big relative to the detector and has a certain range of smaller masses for its pieces. So we're talking here about constituent masses or the size of a small piece of the dark matter. And so Yilda has been doing excellent work in her PhD, which she's finishing soon, thinking about what happens if one of these dark matter composite states comes and intercepts the Earth. And she's discovered a lot of really interesting things. She's discovered that actually when the dark matter composite state hits the Earth and has certain properties, it interacts in a certain way, it'll turn into a big shower of particles, which requires us to go back to our experimental colleagues, by the way, we're theorists, and say, hey, let's design new searches that we can look for this spray of particles hitting detectors, which is going to look a lot different than if you just have one particle coming in and bonking your detector. And I'm getting a little bit ahead of ourselves because I haven't even told you how dark matter is detected yet. But I just wanted to show you an interesting way that dark matter could be. So next I have to talk about where did dark matter come from. And this maybe clarifies, once I go through it, why I think actually the Big Bang rendition, as in the TV show rendition, is a much better representation than the NASA one. So if we look here, what we see are one region that I've marked with this purple dashed line. That's the part of the early universe we don't know about. But we have a lot of great guesses. The green part is the part that we have very well established, and that starts at about 3 minutes. And so the Big Bang, most of the expansion that you see happens on extremely short time scales relative to the age of the universe, which has now been measured pretty precisely at 13.8 billion years. And so if you are looking at something in a Big Bang, it should happen very quickly, and also you should feel like you're inside of it. Because one thing that's important to keep in mind is that it's not that the universe rushed out to where we are now, it's that every point in space stretched away from every other point in space. So all those points rushed out and created the expanse that we're now sitting in. But we were always, or our position is always in the middle of it from the very beginning. And so then we can ask, how do we know all that? What is the evidence we have? Why are we so certain that that's the structure of our early universe? And the answer is, we've looked at a process, which is exactly the process I showed you, where an electron falls into a proton, here represented with 3 quarks, and emits a photon, because it has energy now to do so. And that photon travels all the way to the present time. But as it travels to the present time, it gets redshifted, we learned, because space is stretching apart. And so let me give you a sense then of what it's like to look at those photons from the very early universe when electrons combined with protons in a process that is badly called recombination, because maybe it should just be called combination, because it's the first time those things are coming together. But never mind, we sometimes don't get the naming right. Let me show you a little bit what it's like to measure that. So if we zoom in to a patch of the light that was emitted, and that was a map of all the light emitted from the early universe, what you would see from that patch as the universe evolves is that structure forms in any one of those patches, and galaxies form around those structures. And then as you zoom out, what you're seeing is what's called the Wilkinson Microwave Anisotropy Probe, which went away too fast. Here, I'll bring it back. Will I bring it back? I guess I won't bring it back. So it's a satellite that looks for these microwave photons, which are microwave because they've been stretched so much. And what it's seeing is where regions of space where there are and aren't stretching, how those correspond with where galaxies do and don't form. So there's a lot of data there, and when you tease apart that data, you actually find even more evidence for this Big Bang cosmology. Okay, so now we come to sort of the punchline of this talk, and that is that we don't actually fully know what's going on in this early part of the universe. But what we can say is, we know there's some sort of dark matter or dark boson or something we don't understand about nature yet. It must have been made at some point in the universe. And so we could try to build a collider to make every single possible dark matter candidate in a laboratory. But the truth is, dark matter was already made in the biggest collider, which was the universe. Because the universe, when it was early on, was in this highly energetic state, smashing particles together, making every other particle that we see. And so, in a sense, the biggest collider in the universe that you could possibly make is the universe, just from an earlier time, and that's indeed when dark matter was made. So then, how do we find that dark matter? So this is an excellent TEDx talk by Professor Jana Levin. I will again narrate my way through it and talk to you about how we look for dark matter. But I highly recommend that you go look at Jana Levin's original TEDx talk. It's like 4 minutes long in total. So we have our dark matter states coming from the early universe collider. They're smashing into the Earth, or they're actually probably not smashing into the Earth because they're probably interacting too weakly. We don't know what they are. It's quite nebulous. But we, as particle scientists, we'd like to build our detector for the end point of that collider. And you might think, why don't we just build the detector anywhere? Why don't we just put it in this room? And the answer is there's all sorts of radioactive stuff. There's all sorts of things like potassium, thorium, even a little bit of uranium around that would creep into our detector if we kept it near the surface. So instead what we need to do is find a region underground, deep underground, where all of the radioactivity, which is about to shower down, can't get to our detectors. And so that sets where we're going to put the detector, is as deep underground as we can. And so looking at this detector, you might think, oh, that's the detector, and those are the little detection modules, the photomultiplier tubes. But actually that's not it. You've actually just looked at the shielding for the detector. Inside the detector, you have to put a different material, and on the outside what you were seeing was just the shielding for the interior material. And there are a few interior materials that we use to interact with dark matter. Argon, silicon, germanium are big ones, and then there's something that this video called refrigerant, which would be something like the PICO experiments, exotic sort of mixed material. So you look for the argon, for example, to be hit by a dark matter state, and when it's hit by a dark matter state, it would emit a flash of light. But what you want to do also is shield your entire detector with a ton of water. And the reason you're doing that is because you want to be able to say whether what you're seeing is just something on the outside, like a normal particle, like a muon, or something that actually made it into your detector. And then, of course, just like for the CERN experiment, we're collecting tons of data from all these PMTs all the time, and we're creating better and better shielding around newer and newer kinds of detectors. And we're waiting for this signal to come along. We're waiting many, many years. And this gets back to the society thing I showed you, that every big experimental endeavor requires a lot of contributions. These experiments are becoming very big, not too expensive yet, and we haven't found anything yet, and we're still looking. And so that brings me to Snow Lab, which is really a leading dark matter laboratory in Sudbury, Ontario. And it has a few experiments, including Super CDMS, PICO, NewsG, Deep 3600, which was the experiment featured in that video, of course, that you saw, that you can go learn more about up in the Snow Lab Visitor Center and learn about how each different detector operates. Probably better to talk to the experimentalists about the exact details. I'm a theorist. Okay, so that's bringing me to the end of searching for dark matter using the largest collider in the universe. And here I've shown you what is a plot that we worked together with the experimentalists to make that shows you at very large masses. So this is up at that microbial mass. And it turns out that this Deep 3600 experiment is the best experiment in the world for looking for dark matter that would be about the mass of a little mite, a little bug. And they're doing groundbreaking work searching for dark matter, and we could find it up in that region over to the right, which is a higher mass, somewhat higher cross-section or higher size region. So at this point, I would say we've heard the call to apply the measure to heaven and places the measuring rope on earth. So we've done that in a few different ways, and we're just waiting and trying to figure out what nature actually made in this mysterious dark matter substance. And I'll leave you with both paprika and wasabi dancing around on their newly built captures, which they were happy with in the end. Thank you.